Dear students, welcome back to the second part of my presentation on thin and thick cylinders. At the end of the first part of my presentation, we had just concluded with an expression for the circumferential stress in the wall of a thin cylinder. So, let us try to move on and understand how we get the expression for the longitudinal stress in the wall of a thin cylinder, which is important with respect to thin cylinders. So, if we just try to look at the picture on the screen, we have a cylinder which is subjected to an internal pressure, and understand that what we are trying to look at is a cylinder which is closed at its ends, and we are trying to talk about a situation where the bursting may happen along a cross section which is transverse to the longitudinal axis. So, if we just try to see the picture over there, so the pipe is having some length, and we are trying to imagine that the cylinder is going to burst along section BB, which is perpendicular to the length of the cylinder. So, why does this cylinder burst that is along section BB? It is because of the force induced by the internal pressure on the end wall of the cylinder. So, there is every possibility that the cylinder may rupture in a vertical plane in this cylinder, and we are trying to have a bursting effect in this direction. So, understand that the failure plane or the bursting section is in the vertical direction, which is perpendicular to the length of the cylinder, unlike the previous expression where we had considered a longitudinal section as the plane or the bursting plane when we were trying to derive an expression for circumferential stress. So, I am just trying to show you an video of how a bursting force looks like and how do we arrive at an expression to calculate the longitudinal stress in this case. So, if we just try to look at this video. So, I am just trying to take a section. So, I am just trying to take only the right part of that section, and then I am just trying to slowly rotate it, trying to put it in a 3-dimensional view, and what you are trying to see over there is the free body diagram of the cylinder to the right of section BB, that is a vertical plane. So, if I just try to repeat this video once again. So, please watch carefully. So, the section is there. So, I am just trying to take the right side of that, rotate, and I am just trying to show you the magnified view. So, on the right side, what you are trying to look at is that bursting force acting on the right end wall of the cylinder, and at the cut section you are trying to see the longitudinal stresses being released because of that cutting edge. So, when you write the free body diagram, you have to release the stress at the cut section, and these stresses are nothing but the longitudinal stresses. They are the normal stress, and they are present on the cut wall of the cylinder, right. So, now coming to the two things, again we are trying to talk about the equilibrium equation for this particular diagram, and then we are trying to arrive at a very simple expression that is again for longitudinal stress, which is similar to that of the circumferential stress. So, we just try to look at the animated view over here. So, you can clearly see that the bursting force F2 acting on the right wall of the cylinder, and on the left wall, that is the wall, right, you are trying to see over the thickness, you are trying to see that the longitudinal stresses being developed. Let us try to understand how do we calculate the bursting force in this case. So, the bursting force basically acts over the end wall, and when the pressure is acting on the end wall, it is basically acting over that circular region. And how does one calculate the area of a circle? It is pi by 4 into d square, area of the circle, right? And a pressure P is acting on that. So, the bursting force is the pressure multiplied by the area, circular area. So, it is as simple as P into pi by 4 d square. Now, that is the bursting force. Now, let us talk about the resisting force. Now, this resisting force is because of the longitudinal stress, and this longitudinal stress is acting over the wall. So, let us understand how do we calculate the resisting force. So, I am going to just try to show you a simple diagram on the board. So, if you just try to look at the picture over here. So, we are just trying to take a thin cylinder over here, that is the cross section, thin cylinder, thin cylinder, right. So, that is the diameter and that is the thickness. Please understand, I want to calculate the area of this, area of this portion. Now, because the thickness is small, right. So, we can calculate the area in a very simple way. It is an approximation, but we can just try to get the area in a simple way. Now, I am just trying to cut this cylinder, and then trying to make it as a rectangle. So, I am just trying to equate this as a rectangle, right, rectangle. I am just trying to cut this and then spread it as a rectangle. Now, what is this? It is a thickness. So, obviously, that is T, thickness. Now, what is the length? So, length is nothing but the inner circumference is the length. So, that means we approximately take this as the inner circumference. So, the inner circumference of a circle, it is pi d. So, this is nothing but pi into d. So, all we have is a rectangle whose length is pi d and thickness is t. So, the area is calculated as pi d into t. So, we just try to use this to calculate the area of a circle. This is possible provided you are talking about thin cylinder where the thickness is small when compared to the diameter. So, please understand, this is how we intend to calculate the area in this particular case. So, let us try to come back and look at the expression that we have for the resisting force. So, as you can clearly see on the picture. So, the resisting force P is calculated as the stress, longitudinal stress sigma suffix L into area. So, the area is calculated as the circumference or the perimeter multiplied by thickness. So, perimeter is pi d, thickness is t. So, that is how you try to get the resisting force. So, when you talk about the equilibrium equation, so it is very simple. So, to the left I have P, the resisting force, to the right I have F2. The free body diagram is in the equilibrium. So, I can easily understand that so the resisting force should be equal to the bursting force, or you can just try to say F2 minus P equal to 0, trying to consider the equilibrium along x direction or f suffix x. So, if I just try to take the same picture here, so you can clearly understand I have bursting force to the right, the resisting force over there, and this is how we are trying to apply the equilibrium equation, that is sum of all the forces in the horizontal direction equal to 0 or in x direction equal to 0. So, I have two forces here, to the right I have F2, so it is plus F2, to the left I have the resisting force. So, resisting force is calculated as stress into area. So, stress is nothing but sigma L, the longitudinal stress which is acting on the wall surface, cut wall, okay, section over there. Area, we have just discussed how we calculate the area. It is nothing but the inner perimeter multiplied by the thickness. So, we just try to substitute these two parameters, that is F2 as internal pressure into the area pi by 4 d square, and capital A as pi d inner perimeter into thickness. Okay, you get this expression. So, you need to simplify this and then you get a very simple expression, very similar to that of your longitudinal, that is circumferential stress. So, the expression we have got here is P d by 4T. So, again if you just try to look at this expression, so you can easily understand, as the pressure, internal pressure increases, the longitudinal stress increases. As the diameter, internal diameter increases, the longitudinal stress increases. As the thickness increases, okay, the longitudinal stress decreases. So, that is how you need to understand, right. So, please remember the expression for the longitudinal stress, that is P d by 4T. Now, let us try to talk about the relation between the two important stresses that we have just derived, that is the circumferential stress and the longitudinal stress in the wall of a thin cylinder. So, let us start with the first expression, that is the circumferential stress we have got as sigma c equal to P d by 2T, right. Now, we have the second expression, the longitudinal stress sigma L equal to P d by 4T, right. Now, we just try to compare the two. So, you can easily understand that the circumferential stress is more than the longitudinal stress in a thin cylinder problem, right, because for a thin cylinder, any thin cylinder that we are trying to take, there would be a fixed value of P, diameter and thickness. So, for a given value of P, D and T, so if you just try to look at the expressions, you can always understand the circumferential stress is always larger than the longitudinal stress. But if you just try to have a closer look, you will really understand that, okay, the circumferential stress is 2 times larger than the longitudinal stress, right, correct, because the first one is P d by 2T, the second one is P d by 4T. So, obviously, the circumferential stress is 2 times greater than the longitudinal stress. So, that is a very important information that you need to be aware of. Okay. Now, coming to the next one, we are talking about the maximum shearing stress in a thin cylinder. Now, where exactly we are talking about thin cylinders, that is shearing stress? Right at the beginning, I did mention that we are talking about an element which is subjected to only normal stress, correct. Now, we are talking about shear stress. What is this shear stress we are talking about? So, let me just try to go back to the board, okay, make you understand, okay, what is this shearing stress or shear stress we are trying to talk about. So, if I just try to come back to my element, okay, that we are trying to talk about, I am talking about thin cylinder. So, in a thin cylinder, as we understand, the element has only 2 stresses, that is the circumferential stress and the longitudinal stress. So, if I just try to talk about an element, something like that, okay, right, okay. So, that is the wall thickness, correct. So, I can just try to say, okay, so that is the longitudinal stress that we have here, sigma L, and that is something but sigma C we are trying to talk about, correct. So, it comes to something like this. So, I have a element, right, in plan. I can just try to show the same thing like this, which is subjected to normal stresses sigma L, okay, longitudinal stress, one more stress sigma C, correct. So, I guess this is a problem that we have discussed in compound stresses, right. So, an element subjected to more than one stress, that is here in this case there are two normal stresses we are trying to talk about. So, right now on the boundary you do not have any shear stress, okay, but understand. Okay. So, if you just try to take some plane here within the element, some plane, any plane within the element here inclined at an angle theta, correct. So, please understand that this plane, correct, will be subjected to some normal stress and some shearing stress sigma s, right, normal stress and shear stress. So, what we are talking about is, okay, what may be the maximum shear stress, okay, that would be present within the element, correct, right, is what we are talking about, that is sigma s. That is important, because when you are designing a problem, correct. So, we want this information, okay, that is the shear stress, what is the maximum shear stress, so that you can design, okay, the wall of the cylinder such that the shear stress is within the permissible limit. So, we have an expression to calculate, okay, the circumferential stress, which is nothing but PD by 2T. We have an expression to calculate the longitudinal stress, that is PD by 4T, right. So, with these two values, right, we can always calculate, right, the maximum shear stress, okay, that this element will be subjected to, right, at some plane within the element, right. Okay. So, let us try to understand, okay, how exactly we get this. So, I will just try to come back here, right, okay, with this simple information. Okay, as I just said, the walls are subjected to only two stresses, that is the circumferential stress and the longitudinal stress. And one more thing, both are normal stresses, as I just mentioned, right. The walls are not subjected to shearing stresses, right. So, since the walls are not subject to shearing stresses, the most important conclusion that we are trying to talk about is, okay, these are called as the principal stresses. That means, if you just try to take that element, right, okay, and then try to have many planes, okay, within the element, okay, right from 0 degrees to 180 degrees, right, and then try to calculate the normal stress on each of these inclinations for a given value of circumferential stress and longitudinal stress, the two normal stresses. If you just try to go on calculating, okay, the normal stress present on various inclined planes right from 0 degrees to 180 degrees within the element, and then compare all these normal stresses, right, you will be able to understand that, okay, there will be a plane on which the normal stress will be maximum, and there will be another plane where the normal stress will be minimum, which are referred to as the principal stresses. And please understand, okay, another important thing that you need to understand here is principal stresses act on principal planes, and principal planes do not carry shear stress. So, the inference that we are trying to say here is, okay, since the walls, okay, are free of shear stress, okay, these two normal stresses by themselves will be called as the principal stresses. They are the principal stresses. So, if you just try to compare the circumferential stress and longitudinal stress, we understand sigma c circumferential stress is always more than the longitudinal stress. So, obviously, the maximum normal stress should be sigma c and the minimum normal stress should be sigma L, longitudinal stress, that is PD by 2T is the first normal stress, maximum normal stress, first principal stress. The second principal stress, okay, is nothing but sigma L, which is PD by 2, that 2T, that is 4T, that is the minimum principal stress. So, with this information, okay, so let us try to see how we can calculate the maximum shear stress, okay, in this element, okay, right. Now, please understand, right, in the last presentation, right, when things were discussed under compound stresses, I think one important bookwork, okay, has been presented, which tells you a relation between the principal stresses, okay, and the maximum shear stress. So, the relation is, okay, the maximum shear stress is 1/2 the difference between the principal stresses, right. So, that is the expression I am just trying to give you, that is sigma S max is equal to 1/2 the difference between, okay, the maximum and minimum principal stress. Sigma N1 is the maximum principal stress, sigma N2 is the minimum principal stress. So, in this case, right, so sigma N1 is nothing but sigma C, sigma N2 is nothing but sigma L. So, we are trying to substitute sigma N1 and sigma N2 with these numbers, and then we try to simplify, you get sigma S max. So, you can easily observe that, right. So, if you just try to deduct, okay, PD by 2T with PD by 4T, what you get is PD by 4T, and PD by 4T divided by 2 is PD by 80, and this is the expression, okay, that you need to remember, okay, when you are trying to calculate the maximum shear stress. So, please understand, that is, dear students, so we have 3 important expressions right now. The first one is the circumferential stress, which you just see above the expression of shear stress, that is PD by 2T. The second expression is the longitudinal stress. So, beside that you are seeing that expression PD by 4T, and the last one is the max shear stress, which is PD by 80. So, these are applicable to thin cylinders, that is the stresses in the wall of a thin cylinder, right. Now, having learned these important expressions, so we have another few expressions, okay, that are equally important. So, the first one being expression for change in diameter in thin cylinder. What exactly is this? So, if you just try to take a thin cylinder, right, and subject it to some internal pressure P, right, inside, you can understand that, okay, the cylinder is going to expand, right. Okay, just try to take the cylinder, yeah, put some internal pressure in, that is with respect to, it could be from gas, okay, or it could be liquid, fluid, whatever it is, you just try to put it under pressure, right. Okay, then the cylinder slightly becomes big, right. So, that means what? There is a change in dimensions. Please understand, there are no distortion in geometry. That means a cylinder will again look like a cylinder, bigger cylinder, okay, not get distorted, there are no shear strains, correct, right. So, what are we trying to do here? We are trying to just find out, right, what is the change in diameter, okay, that occurs, okay, when you just try to put some big pressure, okay, in the inside the cylinder. So, let us try to understand how we get this. It is quite simple, you can understand, right. So, there are a few expressions, right. I am just trying notations, I am just trying to make you go through. The first one is sigma C, which is called the circumferential stress, and as we have understood, it is nothing but the first normal stress, that is maximum. The second one is sigma L, which is sigma into, that is the minimum normal stress, which is called the other principal stress, minor principal stress, which is nothing but the longitudinal stress, okay. And then there are 2 strains we are trying to talk about: strain along the circumference, which we call as circumferential strain, and the next one, strain along the longitudinal directions, right. Please understand, these 2 are linear strains, understand, correct. As I told you, when you just try to put bigger pressure, it expands. So, when it expands, right, the circumference also increases, right, then the length also increases. Then we are talking about strain. Strain is what? It is a measure of deformation, right. When there is a change in dimension, right, okay, we can calculate, okay, the strain as what? Change in dimension by initial dimension. So, we are trying to just calculate this along the circumference, correct, and along the longitudinal direction. So, we refer them as the circumferential strain and the longitudinal strain. These strains are as a result of, okay, the increased circumference, okay, and the increased length, okay, of the body. Then we have 2 material properties. The first one is the Young's modulus, okay, which you all know, which has been defined, okay, in the first topic, that is simple stresses and strain, correct. And the second one is another material property, that is the Poisson's ratio. These are generally called as the material constants, right. So, let us try to go through this, okay. Now, first one, let us try to understand how we calculate, okay, the circumferential strain, right. Now, please understand, Okay, the important thing, the first one we need to realize is these are two normal stresses we are trying to talk about, sigma c and sigma l, right. So let me just go back to the board, okay, and again try to make you understand this very simple expression, okay, that we have written. Once you understand this, yeah, in no time you can calculate, okay, the change in diameter, right. So let me go back here quickly. So we have a block, take an element, right, subjected to stresses, say sigma c and sigma l, correct? Is it all right? Now because of this you can understand, right, the element is going to undergo some kind of deformation, something like this, okay. Yeah, there could be even bigger, okay, it can be bigger like this, no problem, okay. It gets modified because being stretched in both the directions, it becomes bigger, right. I would like to just calculate, okay, what is this, okay, change in dimension, that is what is the strain that undergoes in this direction, correct. Now I think this has been clearly explained. So we try to calculate the strain, okay, in this direction as a strain, okay, along this direction, that is the strain in this direction. First component is, okay, the strain due to the axial stress acting in the same direction, okay, then minus, okay, the strain acting, okay, in direction perpendicular to this direction. So that means the first one is, okay, that is sigma c by E, that is, okay, stress by Young's modulus, that is this stress by the Young's modulus minus, okay, the Poisson's ratio times, okay, this stress by Young's modulus, that is the stress by Young's modulus, correct. So this is what we call as the, okay, strain along its axis, okay, which you can call it as the longitudinal strain. This is the lateral strain. So when you are talking about this axis, so that's the longitudinal strain and that's the lateral strain we are trying to refer here, correct. So along the longitudinal strain, okay, it is sigma c by E, okay, the strain in this due to this is nothing but minus mu times sigma l by E. So this forms the basis, okay, in this discussion. So you need to understand this very carefully, how we try to calculate the circumferential strain, okay, due to these two stresses, okay, sigma c by E minus mu times sigma l by E. So once you understand this expression, so I think the rest of the calculations, okay, are really simple, right. So what we do is now we try to substitute, okay, values for the circumferential stress sigma c and the longitudinal stress, that is sigma l, correct. So what is sigma c here? Sigma c is PD by 2t. What is sigma l? PD by 4t. So you need to put them, okay, in the above expression, okay, simplify and then you get this expression, okay, PD by 4TE into 2 times nu, that is your Poisson's ratio, right. So what you are trying to get here is the circumferential strain, right. Strictly speaking, circumferential strain is nothing but the change in circumference by the initial circumference, okay. Basically that's how you can try to call or define circumferential strain at this stage. So it is expressed as PD by 4TE into 2 times nu. Again, so if you just try to look at this expression, so circumferential strain, yeah, it increases, right, okay, when P and D are bore, right, okay, and it reduces, okay, right, with an increase in thickness and an increase in the metal property E is what you normally try to understand, okay. So let's try to see, okay, how we try to link this with respect to the diameter, because what we want is the diameter, right. So the first thing that you need to understand is circumference is proportional to the diameter, correct, right. So how do we calculate circumference? It is pi into d. Circumference is pi into d. Pi is a constant, right. As diameter increases, circumference is going to increase, correct. So now we try to say circumferential strain, right. Please now understand, we can literally equate the circumferential strain with the diametral strain because circumference is directly proportional to the diameter. So, in the above expression, right, it is possible for us to replace circumferential strain epsilon c with diametral strain. What is diametral strain? Diametral strain is nothing but the ratio of change in diameter by initial diameter. Strictly speaking, circumferential strain is the ratio of change in circumference by initial circumference, but we are not generally interested to calculate what is the change in circumference. We are more interested to calculate what is the change in diameter. Now, because circumference is directly proportional to diameter, so we replace circumferential strain with diametral strain, right. So, that is what we are trying to do. So, circumferential strain is also proportional to diametral strain. So, with this understanding, so we can write diametral strain as delta d by d, that is change in diameter by initial diameter. So, already we have got an expression for epsilon c in the last slide. What is epsilon c? PD by 4 TE into there is 2 minus nu is what we have got. So, you can always substitute the parameters on the RHS, get epsilon c. But what is epsilon c? As you can clearly see, it is delta d by d. What we want is delta d. How do we do this interchange, right? So, delta d equal to epsilon c into d. So, please understand, so very simple, right? You want to calculate delta d? Yes, you can always do this, epsilon c into d. What is epsilon c? The circumferential strain. How do you calculate the circumferential strain? Yes, that is PD by 4T into 2 minus mu, right. So, the same way we are trying to calculate expressions, another expression for change in length, right. So, let us try to see this expression, epsilon L equal to sigma L minus C minus nu times sigma C by E. This is very similar to what we have done in the previous case. So, if I just try to go back to the board, right, same diagram, right, in the previous case, right, I was trying to calculate the strain in this direction. So, because I am trying to calculate the strain in this direction, this I can say longitudinal strain and that is lateral strain. But now I want to calculate the longitudinal strain or strain in this direction. So, that becomes longitudinal and that becomes lateral. So, if I just try to repeat this, only change in axis. So, I am going to say epsilon L, that is longitudinal strain. I have taken this as first, sigma L by E minus nu times lateral. So, that is sigma C by E, that is it. All I have done is I have interchanged the circumferential strain, circumferential stress and longitudinal stress here, because first case I was trying to calculate the strain like this. So, that was the primary or longitudinal axis, that is lateral. So, in the second case, so that is my point, that is my line of interest, correct, and that becomes lateral. So, you would always take the first one in its direction and the next stress perpendicular to that, correct. So, coming back to the slide, so I have got that expression. I hope you understand. Now, we do a very similar exercise. What similar exercise we are trying to talk about? Right. We now substitute the expressions for sigma C and sigma L. I guess now we are very familiar. So, sigma C is PD by 2T, sigma L is PD by 4T. Substitute in that expression, simplify, you get one more expression for sigma L, right, and the sigma L, right, is PD by 4T into 1 minus 2 mu. Last time it was 2 minus nu, now it is 1 minus 2 mu, slight change, right. So, that is how I get an expression for the longitudinal strain. Now, this has to lead us to change in length, no problem, correct. So, what is longitudinal strain? Change in length by initial length, correct. So, let us try to equate longitudinal strain as delta L by L, correct. Now, what I want is delta L, I rearrange. So, what is delta L? So, delta L is epsilon L into L. What is epsilon L? You are just seeing that, right. So, epsilon is calculated as PD by 4T 1 minus 2 nu, right. So, for a given cylinder, you know its dimensions, right. What do you mean by dimension? The diameter, the length, right. In this case, length is not required, the thickness, diameter and thickness, right. You know that. You know its material properties, that is Young's modulus and Poisson's ratio, subject to some internal pressure, right? With this information you can calculate the that is longitudinal strain. Once you know longitudinal strain, yeah, what is change in length, for which you need, okay, what is the length of the cylinder, right? You just try to calculate the strain epsilon c, yeah, epsilon L, and then multiply with L, you get the change in length, right? So that's how you need to calculate. So another important expression we have got here is, that is sigma L is PD by 4TE into 1 minus 2 mu. So this brings us to the last bookwork that we are trying to talk about here, that is the change in volume, right? So when you say change in volume, please understand it's the internal volume we are trying to talk about, internal volume where the pressure is acting, right? So it should be very clear, okay, change in volume, what volume, right? It's the internal volume, right, which expands, is what we are talking about in thin cylinder theory, right? How do we calculate the internal volume, right? The area into length, right, circular area, right, pi by 4d square into length will give the internal volume, right? Okay. So what are we trying to do is, we are trying to make a small change, okay, we apply logarithms, right, to both LHS and RHS. Once you apply logarithm, you get this as log V equal to log of pi by 4 plus 2 times log D plus log L. I think we can easily understand. Now apply the differentials, right? So we just try to say delta V by V equal to, yeah, pi by 4 is a constant, yeah, that becomes 0. So we have 2 times delta D by D plus delta L by L. What is delta V by V? I think you know, it's nothing but the volumetric strain. Epsilon V, you can calculate as epsilon V. What is delta D by D? Diametral strain, right, which is equated to circumferential strain. And what is delta L by L? It's a longitudinal strain, right? So we are just trying to equate. Now we have an expression which connects the circumferential strain with the longitudinal strain. So that means the volumetric strain is nothing but, or equated to, 2 times the circumferential strain plus the longitudinal strain. But we are not going to stop here, because we know expressions for epsilon c and epsilon L, right? We now substitute those values. That is epsilon c, as you understand, is PD by 4T into 2 minus nu, and epsilon L is PD by 4T into 1 minus 2 mu. Substitute, simplify, you get one more expression, that is epsilon V is PD by 4T into 5 minus 4 nu, right? So these are important, three expressions, 3 strains, epsilon C, epsilon L and epsilon V, right? Now we are talking about change in volume, right? So we now equate the volumetric strain as delta V by V, right? That is change in volume by initial volume in this case, right? Since you know epsilon V, right, you can always calculate the delta V, right? Or okay, I am going to just move on to the board, right? So I am just trying to use my final expression, that is epsilon V equal to delta V by V, right? Okay. Now we have just derived an expression for epsilon V. I know what is V. You multiply the two, you get delta V. What is delta V? Change in volume, right? Okay. So dear students, I hope you have understood how we are calculating change in volume. Now with this, there is one more important thing that we need to understand. This is about joints. Now please understand that the cylinders, okay, are made of sheets, right? It's not one single sheet you have here, right? It's just like that. Big cylinders, okay, they are connected with number of sheets. Now what is the kind of connection we are trying to have here? So they are in terms of riveted joints, or it could be welded joints. So you are just trying to see, okay, cylinders over there, okay, in the bottom of the screen, correct? So the first picture to the left, okay, we are talking about a longitudinal joint. What is a longitudinal joint? It's a joint present along the length of the cylinder. The second one you are seeing is a circumferential joint, right? So along the circumference, okay, it's not that you have only longitudinal joint or only circumferential joint. Generally you have both, right? A cylinder, okay, has many sheets, okay, so the sheets are connected not only in the longitudinal direction, also in the circumferential direction. So normally we have both kind of joints present, correct. You got circumferential joints, you got longeal joints, right. The next one is the efficiency. How good are these joints? How strong they are? So generally we want the joints to be more stronger than the parent material generally, but okay, that's a possibility. That's a possibility. We can make them stronger, right? But generally we assume them to be weaker, right, than the parent material. So if it is weaker, please understand, right. So then that becomes the critical issue, right. So it becomes very critical. The failure may take place, okay, in the along and there is perpendicular to the joints when compared to that of a parent material. So this is quite tricky. You need to understand. So what we said is, okay, generally pipes are not homogeneous, okay, right, in the sense jointless, okay, they are made of joints. Joints can be both along the longitudinal direction as well as the circumferential direction, okay, they can be present in both the directions, right, and generally we need to make them stronger. It's possible to make them stronger, but in general, okay, joints are weaker than the parent material. So whenever they are weaker, so we have to understand, okay, how weaker it is, and this we can always calculate, okay, by an efficiency term. So what is efficiency? Strength of a joint divided by the strength of the parent material, right. That means your joint is how much strong when compared to your parent material. I can say, okay, 80% strong when compared to the parent material, or 60% strong when compared to the parent material. So I can say 60%, I can say 80%. That's how I can always try to define efficiency, right. It's the ratio of strength of joint by strength of parent material, right. So now we have two joints, one along the longitudinal direction, one along the circumferential direction, right. So you can define efficiency separately for the two joints. So I have what is called as eta L, which says efficiency of longitudinal joint. How efficient is the longitudinal joint, right. Okay. Similarly I can define one more efficiency, that is efficiency of the circumferential joint, that is eta C, right. How good is the circumferential joint when compared to the parent material, right. Okay. Now it's important to note that the longitudinal joint resists circumferential stress, correct, isn't it? If you just try to look at the joint, compare over there, and just try to understand how the circumferential stress is going to act. Circumferential stress acts perpendicular to the longitudinal joint. So please understand, right. So circumferential joint are subjected to, the longitudinal joint are subject to circumferential stress. Similarly, if we just try to go to the next one, on the other hand, circumferential joints resist longitudinal stress, right. So you have the circumferential joint, so perpendicular to that you have the longitudinal stress acting. This is very important for you to understand, correct. What is the first one? The longitudinal joint. When you come to longitudinal joint, perpendicular to longitudinal joint, you have the circumferential stresses acting, okay. In the second case, you have got the circumferential joint, perpendicular to that you have the longitudinal stress acting, right. So you have something now to understand, right, common sense. Which joint should be more stronger, okay, is it longitudinal joint or circumferential joint? Please analyze. I just said circumferential stress acts perpendicular to longitudinal joint, and longitudinal stress acts perpendicular to circumferential joint, correct. And we also have discussed circumferential stress is generally 2 times stronger than or larger than the longitudinal stress. So that clearly makes us understand, makes us to understand that the longitudinal joints should be more stronger than the circumferential joints, correct. So with this understanding, okay, we have a very important connection here, right. If the efficiency of the longitudinal joint is less than 2 times the efficiency of the circular joint, then, okay, please understand the longitudinal joints are more critical. That means there is every tendency or possibility that, okay, the longitudinal joints is going to fail. That means what? Okay, the circumferential stresses, are the one which tries to rupture the longitudinal joints. This is very, very important. On the other hand, right, okay, and here the governing expression, okay, is important. The governing design expression we are trying to suggest in this particular cases, okay. So we are using the expression for circumferential stress. So what is circumferential stress? Okay, without any joint, PD by 40, without any joint it is PD by 40. Okay, because of the joint we are trying to talk about efficiency. Okay, now we try to say, right, sigma c into eta L. What is eta L? The efficiency of the longitudinal joint should be equal to PD by 40. So, the governing design equation becomes like this. So, without joints we say sigma c equal to PD by 40. With joints you bring in that efficiency term, right. So, that is efficiency of the longitudinal joint. So, we write it as sigma c equal to eta L, okay, sigma c into eta L equal to PD by 2T. And another important thing that you need to understand at this point here is, okay, the value of sigma c, right, is equated to the safe or permissible stress of the material. That means you cannot allow, right, the value of sigma c to exceed the permissible stress of the material. So, it is very important. The first important thing is, okay, we have joints. We have joints in both that is along the longitudinal direction as well as circumferential direction. Both have different efficiencies, right. We are talking about a situation where the efficiency of the longitudinal joint is less than 2 times the efficiency of the circular joint. Okay. Under this situation, circumstance, okay, the longitudinal joints are critical. If the longitudinal joints are critical, the circumferential stress comes into picture. So, we are trying to equate, okay, the circumferential joint, okay, with the PD by, that is, we are trying to take an expression of the circumferential joint along with that efficiency. We try to say sigma c into eta L equal to PD by 40 with another important thing, equate sigma c as the safe or permissible stress of the material. Now, similar to this we have one more case. So, case is the reverse. So, that means what? Okay, if the efficiency of the longitudinal joint is more than 2 times the efficiency of the circular joint, correct. So, in this case circumferential joint becomes more critical, right. Circumferential joint becomes more critical is what we are trying to tell you, right. So, if that being the case, then again we have a governing differential equation connected with that, sorry, design equation. So, what is this expression we are trying to talk about? That is sigma L into eta c equal to PD by 40, right. So, you are now considering the expression for the stress acting perpendicular to this circumferential joint, which is nothing but the longitudinal joint, and expression for longitudinal joint is PD by 40. Now, because of the joint we try to bring that efficiency term here. So, you write sigma L into eta c equal to PD by 40, right, and this expression has to be used provided the efficiency of the longitudinal joint is more than 2 times the efficiency of the circular joint. Okay. So, with this coming to the expression for sigma L, right. So, we are now trying to equate the value of sigma L, in this case it is sigma L over there. So, sigma L has to be equated to the safe or permissible stress of the material. It is sigma c, it is not sigma, I mean sigma L, it is not sigma c, right. So, I think we have now finished all expressions, okay, that are required to just take up some simple design problems, right. So, we just try to quickly recollect what we have done, okay, in thin cylinder theory. So, we have just talked about expressions, right, for circumferential stress, expression for longitudinal stress, expression for shear stress, expression for circumferential strain, expression for longitudinal strain, expression for volumetric strain, right. And then when we have joints, okay, how we can just try to slightly modify, okay, our expressions for sigma c and sigma L, bringing in the efficiency of the joint into picture, right. I think we have arrived at an important stage here, right. So, in my next presentation, okay, I will be trying to take some simple examples, okay, with respect to the thin cylinder theory. So, I will be just trying to take some simple typical problems, okay, about 4 in number, right, and I am trying to explain. So, once we finish that, we would be trying to go ahead with the thick cylinder theory, right, and then we would be trying to finish the discussion in my next part. So, thank you students, we look forward to again meet in the next presentation.